Alright, so here we are with the Chapter 4, Section 3 notes on using trig functions, angles, and reference triangles in a coordinate plane. Super. So, taking a look at what we have here, we're imagining the unit circle kind of being on this axis, and this is that 0 degree that we have been referencing. So, what happens is if you are talking about something having a positive angle, you are actually going to, and this is where I need to update my notes just a tiny bit, it's actually counterclockwise. So that means that this direction here is going to be a positive degree that you are moving. So if I say it's rotating 90 degrees, that means it's going to rotate to this side versus to this side. That would actually be a rotation of negative 90 degrees. Anyway, and so then this piece down here is negative angles are actually moving you or rotating counterclockwise. We have things called initial sides and terminal sides. This one is usually the 0 degree side, your initial side, or your x-axis. And then the terminal side is kind of where the angle stops. So when we're trying to form a triangle, for instance. So it would be that hypotenuse. Alright. So, we have something called coterminal angles, and that's because circles go around upon themselves. So, coterminal angles are angles with the same initial and terminal sides, but different measures. So the idea is that, for instance, 90 degrees, if you added 360 to 90 degrees, you'd have 450, and those are actually going to land on that same piece, right? So, no matter how many times you go around the circle, if it still lands with that same terminal side, you can actually have that as what we call coterminal angles. If you're talking about radians, you would, of course, rather than 360, you'd be adding 2 pi. And so this is where sometimes if your answer to sine of whatever the angle is going to be 30 degrees, the answer is actually going to be 30 degrees plus or minus 360n. And that's because you're saying and every other coterminal angle that could be after or before that. So I don't necessarily require that you put this here, but I do require that you understand the idea. So for instance, sine of whatever the thing is, let's see so that I can just get it. What would make 30 degrees? Sine of a half. Alright, so sine of a half is not just 30 degrees. Even though if you plug it into your calculator, it will say 30 degrees, sine of a half can actually also be any iteration of adding or subtracting 360 after that. So, this one here in examples wants you to list some coterminal angles of 30 degrees. So, if we add 360 degrees to 30, we end up with 390. So 390 is also another option. If we add another 360 to that, we're going to end up with something that in my current state I do not want to do in my head. My current state is that of exhaustion. So 750 is also another option, but then you can also subtract 360 as well. And so 30 minus 360 could be negative 330 degrees, and so on. Alright, so these are all options of a different coterminal angle. Then we have 2 pi over 3. And so to 2 pi over 3, we could add 2 pi. The problem with adding 2 pi is that we don't have a common denominator. So instead, 2 pi is equal to 6 pi over 3, and so then we'll actually have a common denominator. So we're going to add 6 pi over 3 because then it has that common denominator, and so one other option is going to be 8 pi over 3. And that's kind of why we don't love radians, just because it is fractions, and you know, I love fractions, but hey. Alright, then we could also take 2 pi over 3 and subtract 6 pi over 3, and we could subtract or add as many iterations of that as we would like, which will give us negative 4 pi over 3. And so again, anyway, these are all coterminal angles with 2 pi over 3. Oh man, alright, here we go. So, we're going to let theta be the acute angle in a standard position triangle whose terminal side contains the point 1, 4, and we need to find 6 trig functions of this. So let's take into account what they're telling us here. Alright, theta is the acute angle, and so that's actually going to be over here somewhere, okay? It's in standard position, meaning that its initial side is going to be here, and its terminal side is going to be somewhere over here. And so how do I find the terminal side? I go over 1 and up 4, and that is the coordinate where this line will continue through. So we need to find the 6 trig functions of this triangle that if I draw it in a way where we can write on it, here's my angle, and I know that I went over 1 to get there and up 4 to get there, right? To get to this point here. So all we would need to do is use the Pythagorean theorem in order to get our hypotenuse, and we would be able to do all of the 6 trig functions. So if we say that a squared plus b squared equals c squared, a could be 4, b could be 1, and c is the hypotenuse we don't know. So 16 plus 1 means that the square root of 17 is our hypotenuse. If we want to do all of our 6 trig functions, remember we have sine and then its flip of cosecant. Then we have cosine and its flip of secant. Tangent and its flip of cotangent. So based on where the angle is sitting, this is your opposite, this is your adjacent, and of course this is the hypotenuse. And so our sine is going to be opposite over hypotenuse, so 4 over the square root of 17, and then of course the flip over here for cosecant. Cosine is going to be 1 over the square root of 17, and then the flip for secant. And then tangent is going to be opposite over adjacent, so 4 over 1 or 1 over 4 for cotangent. So looking at how this is set up, again, acute angle, right? Because every other angle, if one of them is 90 degrees, has to be acute. So acute angle in standard position, whose terminal side contains the point 1, 4, meaning in order to get to that point, you'd have a side length of 1 and a side length of 4 to get there. And then we use Pythagorean theorem to get the missing length. Alright, so the next one here, we're going to let theta be any angle in standard position whose terminal side contains the point -3, 4. So as we're drawing this, again, here is our axis. Remember, our terminal side is here. However, what happens is we end up kind of using this entire thing as a terminal side. And so since we are trying to look for a triangle that has the point -3, 4, we are actually going to be using this piece as its base that would meet our triangle at 90 degrees. So again, this is kind of the angle that formed to get there, but our acute angle is going to be inside here. So breaking it down in how it works to get there, we have -3 to get to this piece here, 4 to get to this point here, and we're looking at the angle over here, which means that this will be our opposite measurement, this will be our adjacent measurement, and this will be our hypotenuse. The negative does matter. It will tell us if it's oriented in quadrant 1 or in this case quadrant 2. And so now we can find our 6 trig functions. So we've got sine, cosecant, it's not a C, cosine, secant, tangent, and cotangent. In order to fill in these pieces, we are going to need to do the Pythagorean theorem. So one of our side lengths is 4, another is -3, one of our legs to get the hypotenuse of C. So 16 plus 9, so 25. And so the square root of 25 is going to be a c of 5. Of course, because it is a Pythagorean triple, we could have seen that, but of course with that negative, it's kind of interesting to see how that works out. So our sine is going to be opposite over hypotenuse, so 4 over 5. And then, of course, the flip for cosecant. Our cosine is going to be adjacent over hypotenuse, and so this is where someone would then be able to recognize that this is not in quadrant 1 because we have our negative. And then the tangent is opposite over adjacent, so 4 over negative 3. The negative can be on top, bottom, or outside, so it doesn't really matter there. And then, of course, the flip of negative 3/4, which is not visible. There we go. All right. So the next ones, we're going to determine if each of the following trig functions is positive or negative without using our calculator. So the idea is that we would use the unit circle and then be able to kind of rotate in our mind in order to see if the y value or the x value or the ratio of the y over the x would make a positive or a negative value. So if I'm thinking of 173 degrees, imagining the unit circle where 0 degrees is here, 180 is here, 90, and 270. If I need to use 173 degrees, I am not quite to 180, right? So I'm in this quadrant over here. And in this quadrant over here, our y values are all positive, just like in this quadrant. Over here, our y values are all negative. And then for our x values, over on the side, they're all negative. But over on this side, they're all positive. So, taking a look at sine of 173 puts us in this quadrant, which means that the sine or the y value is going to be positive. The cosine of 173, notice my x value, it's going to make it negative if we're again in that same quadrant. Tangent of 200 puts you not quite to 270, right? So we're in quadrant 3. And so that means that we need to take y and x and divide them. Dividing two negatives makes a positive. So I don't know why I put 0, positive. The next one is 7 pi over 4. This is where it's going to be helpful to have your unit circle out. So if we go to our unit circle, we can see that 7 pi over 4 is down here in quadrant 4. And so if it's down here and we're looking for the sine, which is the y value, we're going to say that that would be a negative outcome. Again, you can just type this into your calculator in radian mode and you will get a negative number and be able to say that, but of course we're trying to visualize and understand the unit circle here. Cosine is our x value, so if we find 2 pi over 3 in the unit circle, 2 pi over 3 is right here, and so we're in quadrant 2. And so in quadrant 2, we end up with an x value, or our cosine, of negative. And then the last one, 4 pi over 3. 4 pi over 3 is in this third quadrant. And so as a ratio of our y over our x, because that's what tangent makes, again, a negative over a negative will make a positive. Alright, so here is our definition of a reference triangle. This is what we've been making kind of this entire beginning of the notes here. So a reference triangle is a triangle formed with the terminal side of an angle and the perpendicular line dropped to the x-axis. So we kind of mentioned that this is kind of our home base, and then when we think about our angle, it's going to that angle, but then using the acute measure of it. So depending on whatever hundreds of degrees it is, we're trying to find the acute angle that makes up that right triangle, with the angle being the one closest to the origin. This one here is, instead of getting us to find the angle given the 2 points, we're actually going to get the point from what they're giving us. So we're going to name a coordinate on this terminal side. So what points could potentially be on this terminal side? And in order to do that, we're going to use our knowledge of this angle measure. So as you can see, 11 pi over 4 is given, and of course that's going to be in radians, so it's probably best if we just start out by converting that into degrees. So we multiply by 180 over pi in order to get our degree. Interesting degree because it's 495 degrees, but of course that's not really helping us out. So if we kind of rotate it back on its coterminal idea, it also could be 135 degrees. That's a little bit easier for us to visualize what that means. And so if this piece here is 135 degrees, then what is this acute angle measure? Well, it's 180 minus 135, so 45 degrees. So we now have a right triangle with 45 degrees here, and then, well, because we know it, 45 degrees there. And so if we reference our unit circle at a 45 degree angle going into quadrant 2, a point that could be on that line that we know of is going to be the one that goes through this point, right? Because this is 45 degrees here. So that means that this coordinate point, no matter what line is happening, if you have a 45 degree acute angle, is going to be negative square root of 2 over 2, comma square root of 2 over 2. Alright, the next one they want you to evaluate sine of 13 pi over 6 without using a calculator. Probably best to convert this into degrees, so 13 pi over 6 times 180 over pi. Makes 390, but of course that's not one of the unit circle degrees, so it's actually 30. So we are saying that we're actually looking for sine of 30 degrees, meaning the y value at 30 degrees. So going to our unit circle, the y value at 30 degrees is a half. So pretty much every time they're saying without using a calculator, you always want to go to the unit circle. And so that was a half as our answer. Alright, the next one, same process. We have 17 pi over 4. And so 17 pi over 4 is, again, easier to look at as a degree. And so we have 765, but that's not on the unit circle, so we make its coterminal angle, which is not that one yet either. And so it's 45 degrees. And so we want the cosine of 45 degrees, which means that we want the x value at 45 degrees. So the x value at 45 degrees is here, x value square root of 2 over 2. Alright, continuing on here, we have cosecant of 90. Interesting part about cosecant, of course, is that it's actually sine, so we're looking for 1 over the sine of 90. Sine is your y value, and so we're looking for the y value at 90 degrees. Y value at 90 degrees is 1. And so we have 1 over the sine of 90, which is 1 as well, and so 1 is our answer for the cosecant of 90. We also have our idea of quadrantal angles. I know, it's a weird quadrantal angles. Wow, that's getting me today. Whose terminal sides lie along one of the coordinate axes. So quadrantal angles are basically this one here, and so it's very hard to say what, for instance, quadrant does 90 degrees lie on, right? And so in order to answer what quadrant 90 degrees is in, you just say it's quadrantal because you don't actually have a quadrant. So most people would say something like, it's between quadrant 1 and 2, but it's because they just didn't know that. All right. So next one here, we're going to evaluate without using a calculator, again, by using ratios in a reference triangle. So notice that they're giving us that cosine of this triangle, whatever it happens to be, is 3/5, meaning that because of SOHCAHTOA, we have an adjacent side that's 3 and a hypotenuse that's 5. They're also telling you that cotangent, meaning 1 over tangent, or the inverse of tangent, the flip of tangent is going to be negative. Meaning if we go back to this piece here, when will tangent, because cotangent and tangent are the same division idea, when will tangent in a fraction here equal a negative number? And so in that case it could either be in quadrant 4 or quadrant 2. And then we go back and we say, okay, well, if we're going to have an adjacent side that's 3 to this angle that we have here, that's going to mean that this side is 3 or this side is 3. And of course, in order to go backwards, we can't have a positive 3. Oh, sorry, I was drawing that backwards because that's quadrant 1. Beep. And so if we look at both of these, quadrant 4 here does have a positive 3 adjacent length, but if we were looking at quadrant 2 here, that can't be it because you'd actually need a negative, and we don't have that. So in that case, our reference triangle is upside down, for lack of better caring if it's oriented that way. And then 3 is going to be this adjacent side. And then we also know the hypotenuse is 5. And then, of course, because we've mentioned it so many times, the Pythagorean triple means that this is going to be 4 for your opposite. So from that, we can go ahead and answer what is sine of theta. So sine of theta is your opposite over your hypotenuse, so 4/5. And tangent is your opposite over adjacent, so 4 over 3. And now that I'm thinking about it, it matters that this is negative because it's going down, so it's negative 4 over 5 and negative 4 over 3. All right, whoops. All right, so here's our interval notation. We're going to write 2, 100 using inequalities. So this is a notation that the book tends to use. And so what happens is it looks like a coordinate. So as we may start to look into the answer key in our book, which is usually what I have highlighted and pasted in the answer keys on HeadRush here, the idea is that anytime that you have a open parenthesis, that's actually the same as a less than or a greater than symbol. If you end up having a bracket symbol surrounding a number, that actually is interpreted as a less than or equal or a greater than or equal to. And so rewriting this first using inequalities actually means that 2 and 100 are being used. We don't really know what variable it is, but that's okay. And we're talking about the fact that it's between 2 and 100. So this is kind of our inequality notation for this bracket notation. So the book's notation or this bracket notation is going to show up. And so when it says things like, what's the interval? It might say it's between 2 and 100, and it might actually say it in this notation versus in the notation that we're pretty used to. The other thing, and we've kind of already done it in our previous page here, is actually identifying if things are positive or negative. So we kind of already did it, but your cosine or your x value is going to be positive over here. Over here it's also going to be negative. Down here your x value is negative, and over here your x value is positive. For y's, The sine over here is positive. The sine over here is also positive. Negative to get down there, and negative there. And then the tangent is the fraction of both. So a positive divided by a positive is positive. Negative would happen here. Positive would happen here for tangent, and negative here. So just something to kind of reference as you're looking for answering questions of the type where it asked you if it was positive or negative, like these ones. All right. So we do have an assignment on using this, and of course it's always good to have your formula sheet out, and then of course that unit circle for reference. So that is our notes using trig functions, angles, and reference triangles for Chapter 4, Section 3.